Welcome back, y'all. This is Jeff. In this video, I'm going to give you a toy general linear systems problems. I hope you have your rotten tomatoes ready to throw at me. I'm going to sin, which is I'm going to give you a matrix problem. My question always as a mathematical thinker is, where would this type of problem arise in quote-unquote real life? And my statement is only in a mathematical classroom would something like this arise, because it's constructed to highlight some of the features of the solution mechanism, not to actually help you understand how math is applied in your life. With that in mind, please bear with me. We're going to focus on the ideas behind the calculations, not the modeling that would give rise to this. But let's assume that we have the following general linear systems problem. We have a integer coefficient matrix. This is going to be a 3 by 5. We also have an unknown vector x, which is a 5 by 1. And we have a known right-hand side vector, which is a 3 by 1. So the dimensions all check out. The inner dimensions must agree. Yep, we got it. So from that standpoint, what we're going to try to do here is transform the original ax equals b into an equivalent system ux equal y that is algebraically more beautiful. Just like we did in the non-singular case, the first thing that we do is we identify the leading entry in row 1. In this case, we get lucky because the first entry, the entry in row 1, column 1, is non-zero. We'll call that pivot position 1. And then what we want to do is use that pivot value to annihilate, to get rid of the sub-diagonal elements. I can actually use the number 3 to do that, and from the standpoint of numerical linear algebra, that's probably the smartest way to go. But I'm going to claim, if I use that number 3, fractions are going to show up throughout the rest of this problem. And to be honest, fractions are kind of a headache from the standpoint of hand calculations. So in order to make the arithmetic easier, why don't we swap rows 1 and 2 so that my pivot is this very, very beautiful number 1. Here I am. I have my matrix A, and I want to swap rows 1 and 2. To do that, I'm going to use an elementary matrix called a transposition matrix. Other mathematicians might call this a permutation. It's the permutation that sends 2 to 1 and 1 to 2. Check it out. In row 1, I'm going to grab 0 copies of the first row, 1 copy of the second row, 1 copy of the third row. So that takes row 2, puts it up to row 1. In row 2, I'm going to grab 1 copy of the first row, 0 copies of the second row, 0 copies of the third row. That grabs row 1, puts it down to row 2, and then the third row is left alone. 0 times that, 0 times that, 1 times that, third row stays alone. If I do that elementary operation to the left-hand side of my matrix, I must do the same elementary operation to the right-hand side of my matrix, because this is an equation. Whatever we do to the left-hand side, we should also do to the right-hand side. That leads to an equivalent equation where rows 1 and 2 are swapped. And the way that we did that swap was through that elementary matrix. Let's go ahead and see how we can use an online calculator to do this. In this case, I'm going to type in Octave online. Octave is an open source equivalent to MATLAB, which is really useful if you don't want to have to purchase a MATLAB license for the first state. We're going to go ahead and CLC means clear the screen. So I just told Octave to do that. Let me go ahead and store my matrix. I'm going to change the window size so that everybody can see this. So I'm going to store this matrix A, and the way that I do that is -3, comma 6, comma -1, comma 1, comma -7, and then I use a semicolon to say I want to go down to the next row, and then I'm going to do 1, -2. I don't have to use a comma to delimit individual entries, but I'm going to do that just for good form. 3, -1, semicolon for the next row, 2, -4, 5, 8, -4, and I'm going to go ahead and close my matrix. Let me go ahead and check that this matrix is indeed the one that I want. And the way that I'm going to do that is just type in A, and now I want to check -3, 6, -1, 1, -7, 1, -2, 2, 3, -1, 2, -4, 5, 8, -4. Next thing I'm going to do is I'm going to store my right-hand side vector, which looked like this one. And that's going to be negative 13, 6, and the next row is going to be 13. And then we just wanted to store E1, and E1 was actually basically all zeros. So there's a zeros function that populates in all zeros. And then what I'm going to do is entry 1, 2 of E1. If we look back at this thing, let me move that out of the way here. So notice entry 1, 2 is 1. Entry 2, 1, so E1, I'm going to go into entry 2, 1, and I'm going to put the number 1. And then the third entry in the third row and third column is going to be 1. So now I have my matrix E1, and check this one. If I multiply E1 times A, and then I multiply E1 times B, indeed, that swapped the first two rows just as we had claimed in this thing. And because I did the same thing to the left-hand side, I also did to the right-hand side. One comment, some of you that learn linear algebra from somebody that's not out of their mind, you probably do this thing called augmented matrices, and that's exactly what's happening. See, the first 5 columns I'm doing to A, and then I'm doing the same operation to B, and that's based on the algebraic property, whatever I do to the left-hand side, I should also do to the right-hand side. So the first thing that we did is we swapped the rows. Now I'm going to use this as my pivot position, and I'm going to say, hey, I want to use that pivot to annihilate this first entry. We've seen that we can do that via shear matrix. To get the entry in 2, 1 of that shear matrix, we're going to take this number, put a negative in front of it, and divide by the pivot. So that's negative 3 is positive 3, divided by 1 is 3. In other words, I'm going to multiply the left-hand side by this shear matrix. Notice that when I do that, I grab 1 copy of the original first row, so I don't touch it. I don't touch the third row, but I take 3 copies of the first row and add that to 1 copy of the second row. That's what that linear combination tells me. That indeed, 3 times 1 plus 1 times negative 3 is 0, so that will annihilate that one. Anything that I do to the left-hand side, I must also do to the right-hand side of this equation. I'm going to make a claim that when I actually go run and do that calculation out, I get the following matrix arising. And don't trust me. One of the major claims that I like to make to my students is never trust your teachers. This is why a calculation machine is really, really nice. In this case, we want to make this matrix here. So I'm going to go ahead and say that this is the identity matrix, the matrix with all ones on the diagonal and zeros everywhere else. And then the additional information that I have is that the entry 2, 1 should be 3. Okay, so now I'm going to go ahead and write E2 times E1 times A, and I expect that to have a 0 in the position that I wanted, which is exactly what we've said here. Notice that when I did that, it actually canceled out this element too, as we see on screen. Not only do I have to do the left-hand side, but I also have to do the right-hand side. And you'll notice those are the exact calculation that I've produced. Next step is we're going to reuse this pivot element to zero out everything under that, because the whole idea is we want to put it in special form. We're thinking row echelon form or reduced row echelon form. In order to do that, I'm going to use a shear matrix. Entry 3, 1 is going to be negative 2 divided by 1. In other words, I'm going to use this shear matrix multiplying on the left-hand side. If I multiply that equation on the left-hand side by that shear matrix, I should also multiply the right-hand side by the same shear matrix, because anything I do to the left, I should also do to the right. Let's go ahead and store that third elementary matrix. We're going to take the identity matrix, produces the diagonal one, and then the third row, first column of that thing looks like it's going to be negative 2. And now I'm going to go ahead, in order to go backwards, I just push the up button. So I push the up arrow on my keyboard. And that's nice because I can recall previous commands that I've already run in Octave. That's the same thing in MATLAB. Now I've zeroed out that element as such. That one also disappears, and that has to do with the linear combinations of those rows. Do the same thing to the right-hand side vector B. And I get that matrix. Check it out. This is starting to look like the stair-step form that we desire in row echelon form, except that I have that 0 under that pivot position. I'm going to say again, if I were to use that number 5 to cancel out that number 1, I'm going to be left with fractions. I could either permute the rows, so swap those two rows, or I could actually hit this with a dilation matrix to turn that to 1. And that's exactly what I'm going to do in this situation. I'm going to hit the left-hand side by a dilation matrix to turn that pivot to 1. If I hit the left-hand side by that dilation matrix, I should also hit the right-hand side by the same matrix, because anything I do to the left, I should also do to the right. That's called the rules of algebra. Let's go ahead and store that elementary matrix. So in this case, we're going to go ahead and say this is the 3 by 3 identity matrix. And then we're going to overwrite the entry 2, 2 with the number 1 divided by 5. Now, when we go ahead and push the up button, I'm going to get to the third to last command that I ran. Oh, sugar. So let's go, this is going to be E4 times, that will give me that number that I wanted to be 1. It also scales, because it scales the entire row, it scales that down by a fifth and down by a fifth. If I do that to the left-hand side, I should also do that to the right-hand side. Now, I'm going to claim this multiplication yields the equivalent linear systems problem, and we're in the exact position that we can now highlight pivot 2 and use pivot 2 to annihilate everything under that pivot in that column so that it gets closer to row echelon form. In order to do that, we're going to use another shear matrix. -1 divided by 1 is -1. So we use this shear matrix on the left-hand side. Can you guess what I'm about to say? Anything we do to the left-hand side, we must also do to the right-hand side. That's called augmented matrices in many people's classes. Now I'm going to use that multiplication. Let's go ahead and do that via Octave. So E5 is going to be the I of 3, 3. And then I know that the entry in 3, 2 should be -1. And now I'm going to go ahead and call my sequence of multiplication. So this is going to be E5 times E4 times E3, blah, blah, blah. Indeed, check that out. When I multiply by this shear matrix, this elementary matrix, that entry goes to 0 as seen on screen. And when I go ahead and multiply B by that sequence of matrices, I get something that looks like this. This last number is basically 0. E to the -15, that's 1.776 times 10 to the -15. I have a lot to say about round-off properties. If you're interested in that, I have a nice sequence of YouTube videos on MATLAB, and we talk all about the scientific computation principles of storing numeric data, etc. But for our purposes, just that's 0. So in other words, what ends up happening is when I execute this multiplication, I get this equivalent system. This is the exact stair-step structure that we hope for in row echelon form, but I want to show you all something that's kind of unique, which is reduced row echelon form assumes that this value is 1. I actually set myself up by doing a dilation to get that value 1 as a way to show you how to do that. And then it also assumes that in any pivot column, anywhere where you have a non-zero leading entry, all other elements of that column are 0. We haven't talked a lot about how to do row operations upwards, but I want to show you how I would do that in this case to show you how I turn this from row echelon form into reduced row echelon form. Specifically, this is the thing I want to zero out. I want to do it with that pivot. So I put a negative on that value, divide by the pivot entry, and then that entry will go in 1, 2. For more information, you can see my videos on shear matrices. I spent quite a lot of time developing that theory in those videos. In this case, what I'll say is I can set this elementary matrix as determined in my equation there. The entry 1, 2 is going to be -2. And then when I go ahead and multiply my sequence of elementary matrices by my original equation, let me go ahead and put that to be A. And then I come over here, E6 times. Indeed, that entry goes to 0. Same thing over on the right-hand side, multiply B. I get 4, 1, 0. That leads me to the equivalent linear systems problem that is now in what we call reduced row echelon form. It has this very, very famous staircase process. It has a right-hand side that is appropriately transmitted. I will say that augmented matrices are literally exactly what we're saying. Anything you do to the left, you have to do to the right. It's just done in kind of a sloppy way, in my opinion. So I would get the same kind of value out for my right-hand side vector if I did it augmented form. And once we have it in this form, the next lesson, in lesson 18, we're going to talk about how we construct general solutions or the entire solution set to this linear system using row echelon form. I can't wait to share with you how to use this form to get general solutions. I'll see you in the next lesson.